Temperature is one of the parameters that most affects chemical reactivity. The rates of reaction respond to it. The equilibrium composition changes with it. Let's concentrate on the latter and see how we calculate changes in Gibbs energy, enthalpy and entropy of reaction, and then relate these to the equilibrium constant and how it changes with temperature. The molar Gibbs energy of each reactant and product changes with temperature in proportion to the negative of its absolute molar entropy. Therefore, the Gibbs energy of reaction is also temperature dependent, as are the enthalpy change and the entropy change associated with the reaction. With all of these parameters changing, is there any way to make sense of it? Recall that the Gibbs energy change tells us which way a system at a certain composition wants to change. There is a thermodynamic driving force to minimize Gibbs energy such that delta G goes to 0 at equilibrium. It is the value of delta G naught that determines the equilibrium constant K. Delta G, in turn, is determined by the changes in enthalpy and entropy according to delta G equals delta H minus T delta S. If we look at the summary of equations in Chapter 9, we see a pretty intimidating list. But once we know how to decipher and dissect it, it's not so bad. First of all, note that the CRC handbook and the NIST webbook both contain lists of thermodynamic values at 298 Kelvin, namely values of the Gibbs energy and enthalpy of formation, the absolute entropy, the heat capacity are all to be found there. And from these values, we can find the Gibbs energy of reaction as well as the entropy and enthalpy changes with reaction. To use these tables and equation, recall that IUPAC defines stoichiometric numbers as signed quantities, with products positive because they're formed during a reaction, and reactants negative because they're disappearing. Therefore, each one of these summations simply means that you subtract reactants from products. But don't forget to multiply each term by the magnitude of the stoichiometric number before you add and subtract. As always in thermodynamics, start with a balanced chemical reaction, including phase designations. Let's start with let's take the water gas shift reaction to produce CO and H2 from methane and water. Delta G equals delta H minus T delta S. So given delta H of formation and absolute molar entropies, we calculate delta H and delta S for the reaction from the summations that we've just discussed. Don't forget to multiply those coefficients, and remember that the pattern is the same for both delta H and delta S. We're going to take the coefficients from the products, multiply our values of delta H of formation, whoops, that should be an F down there, of formation for each one of these from the table, and then we're going to multiply the reactants by their stoichiometric coefficients. We're going to sum up the products, sum up the reactants, and subtract reactants from products. The same pattern works for delta H and for delta S as well. Upon substitution, we find delta H is 205.9 kilojoules per mole, delta S is 214.7 joules per Kelvin per mole, and then using delta G equals delta H minus T delta S, positive 141.9 kilojoules per mole for delta G means that at 298 Kelvin, the reactants are favored at equilibrium. all of this is at 298 K. If the temperature is changed to 1073 K, we don't have tabulated data for that. So we need to correct delta H and delta S. Let's do that here by assuming that the change in the standard molar heat capacity at constant pressure for the reaction is constant with temperature. This allows us to calculate, using that same pattern, not only the value of delta Cp, but it also allows us to pull delta Cp out of the integrals that describe the temperature dependence of delta H and delta S. Then we obtain the following two formula with quite similar formats to calculate how delta H and delta S change with temperature. You take your reference value at 298 and you add a correction term, which is delta Cp times delta T for delta H, or delta Cp times the log of T2 over T1. T1 is 298 Kelvin, T2 is this 1073. Therefore, we obtain new values of delta H and delta S. Again, delta G equals delta H minus T delta S, and now negative 52.2 kilojoules per mole at 1073 Kelvin. The products are favored. We can relate this all back. Now that we have the values of delta G, we can calculate the value of lnk as well. Summarizing, the temperature dependence of thermodynamic quantities and the equilibrium composition can be obtained by using these important and compact equations.